start recording. So let's start. Well, last week, where did we stop last week? Let me see. Okay, English exercise. Well, last time. So we did a problem, which was the problem number. Okay. Okay, it was the ampere meter. Okay, the current transformer. Well, today we will start the new topic, the eddy currents. So, okay, let me write in red. Eddy currents. Well, what does eddy currents mean? In general, eddy currents are the same as we have discussed before, the same currents which occur due to the change of magnetic field, and the only difference eddy currents occur in the volume of conductors. Well, now let me show you the demonstration. So okay, here okay, in the figure A, the situation is similar to the situation that we have already discussed in past lectures. We have a closed loop and we have the magnetic field crossing this closed loop, and the magnetic field is changing with time. Because of a change of this magnetic field, there occurs current I in the closed loop. Well, in the case of conductors, when the conductor is not linear but volumetric, let's say in the figure B, you can see the cylinder conductor in the form of cylinder, and magnetic flux density of B going through our conductor, and inside the conductor there occurs volume currents. So pay attention here. In the case of A, we needed a closed loop in order to occur a current I. However, in the case B or C, B and C are the same. We have a volumetric conductor, and charges, not charge, electric current occurs in the volume of our conductor. Well, inside the volume of our conductor. And these situations also be the situations shown in the figure B and C also can be described with the Faraday's law, and the only difference is in the situation A we have so-called linear conductor, and in the case B we don't need linear conductor, and electric current occurs in the volume of our conductor. Yes, I have started the recording. I have started. Yes, it's going. Okay, or let me let's read a definition for eddy currents. So the figure A, if the loop is closed in a circuit, the induced electric motive force produce an induced. Okay. Sorry, okay. Let's look to the figure B. Sorry, I forgot the idea that I was saying. Let's look the figure B, where a cylindrical conductor is placed in the changing magnetic flux density. Okay, we don't have a loop here. We don't have a loop. We have only one conductor, but we can see the cylinder as being composed of thin short circuit cylindrical loops. Okay, if you look at figure C, it is shown our cylinder is composed of thin short circuit cylindrical loops, and each one of these loops will have an electric motive force that produce an induced current in each loop. Well, the application of eddy currents is okay, very diverse, and one of the applications is in induction heaters, or okay, here you can see another demonstration of eddy currents. So if we have some volumetric conductor, inside this volume occurs eddy currents because of the change of magnetic field. These currents are the same as we have discussed in previous lessons, which are induced because of the change of magnetic flux. So here we can see the demonstration of the application of eddy currents. So we have so let me use a red one. We have a coil here, and this coil produces alternating magnetic field, and this field generates alternating magnetic flux, and inside the coil we put our conductor, in this case metal piece, and due to the change of magnetic flux inside our workpiece, there occurs eddy currents inside the metal piece, and these eddy currents are in fact the electrons that are moving, and these electrons make our metal piece to heat up. And the one of the applications of eddy currents is induction heater. Induction heaters. You may read about induction heaters also on the internet. Well, if we clear. If we go back to our lecture, so let's see one example. Let's see any examples. Okay, example 10.11. Let me copy the figure as well. So we go to here. So let's read the problem. The problem is saying a circular disc of radius d equal to 100 millimeters and thickness of c equal to 1 millimeter is placed in a uniform AC magnetic field as shown in figure. So the magnetic flux density varies as b equal to b0 sine omega t and direct perpendicular to the disk. So in the figure we can see the situation. Okay, the conductivity of the disk is sigma 10 to the 7 Siemens per meter, and the frequency is 50 Hertz. Amplitude of the magnetic flux density is 0.2 Tesla. It means, okay, B0 is 0.2 Tesla. So we need to calculate the instantaneous power dissipated in the disk due to the induced currents, due to the eddy currents. Assume the magnetic field is not modified by the induced currents and the field remains constant throughout the disk. So we said if we put some conductor, in this case the very thin cylindrical or very thin disk, if we put this conductor in the magnetic field with changing flux density B, inside the disk there occurs eddy currents, and these eddy currents start to heat up our disk. We need to calculate the instantaneous power due to the eddy currents. Instantaneous power dissipated in the disk due to the eddy currents. So what we do? First of all, let's reduce our problem into the linear case. It means, okay, let's look to the figure B, where we took only a portion of the disk with radius r and thickness dr. We took only the portion of the disk which is a ring, and this ring is obviously a closed loop. Obviously can be can be assumed as closed loop. And let's first calculate the flux going through this going through this ring of radius r. Okay, we know flux equals to B multiplied by surface area of the loop, and B surface area can be written as PR squared, and B can be written as B0 sine omega t. Yep. And in order to find the electric motive force, we take the phi over the t, and this will be equal to okay, I'm taking the modulus of dphi over dt because now I'm interested only about the value of electromotive force. I'm not interested in the direction or in the sign of the electromotive force. So dphi over dt will be omega p r squared b0 cosine omega t. Okay. Okay. Now, maybe I'll move it here in order to have more space. So, okay. Now, we derived the expression for electric motive force. And now to calculate the power, we need the resistance of the ring. The resistance is calculated for a ring of length 2πr and cross-sectional area equal to C by dr. Okay, the resistance equal to length of this ring equal to 2πr and cross-section area of this ring is let me write here. Cross-section area of this ring can be written as the thickness of the disc is C and thickness of the ring is dr. C multiplied by dr. Okay, now 2πr over sigma multiplied by cross-section area of the ring. Okay. Now let's compute the first. Let's derive the expression for power. Okay, we've derived the expression for electric motive force inside the ring and the resistance of the ring. Now, in order to find power, I'm writing dp because the differential power which is dissipated in the ring and the total power which is dissipated in the disk will be just pt and will be the integral of dp. Okay, the differential power dissipated in the ring is will be equal to electric motive force, or V. So let me write electric motive force squared over R. Electric motive force is equal to dphi over dt and is equal to omega p r squared b0 cosine omega t squared, and R is equal to 2 p r over sigma c dr. And okay, this will be equal if we simplify everything and move everything. So let me okay, let me copy first this and then I will continue here. So okay, p and p squared simplifies, r and r to the fourth power simplifies, this one goes up, or let me draw here, and what we have omega squared pi p r to the third power b0 squared multiplied, so multiplied cosine squared omega t multiplied by sigma c dr over 2. Yep, omega squared pr to the third power sigma c cosine square omega t dr over 2. And okay, we found the expression for differential power dp, and the total power dissipated in the disk will be the integral of the pt, and which is okay, omega squared p r to the third power sigma c multiplied cosine squared omega t over 2 dr, where r changes from 0 up to the radius of our disk was d. Up to the d, and this equals 2. Okay, omega squared p sigma c cosine square omega t are the constants, and we need to do integral of this the only variable in our equation is r to the third power. Okay, if we integrate it and put instead of r d, what we have, we will have omega squared p d to the fourth power sigma c cosine squared omega t over 8. So okay, let me move this also here. Okay, now what we have, if we put the numeric values, what we have, our power will be equal to omega square. Omega is equal to 2 multiplied pi multiplied by frequency. Frequency was 50 hertz multiplied by p multiplied d squared. D was 0.1 meter or 100 millimeters. This means 0.1 meter square multiplied sigma was 10 to the 7 multiplied c was 1 millimeter, it means 10 to the minus 3 multiplied by cosine square. I'm writing omega t just not to write one more time omega, and the power will be equal to, if we compute everything, power will be equal to 1550.3 multiplied cosine squared omega t. Okay, the power dissipated in the disk is equal to this value, 1.5 kilowatt multiplied cosine square omega t. As you can see, the peak value is 1.5 kilowatts. As you can see, for the dimensions of the disk, the power dissipated is quite large, and this leads to the quick heating of the material of disk. So the second part of the problem. So what is the peak power loss at 100 Hz under the same assumptions? Now we need to change only the frequency. So this is the expression for our power. Okay, copy. Okay, this what the fuck? Okay, so this is the expression for power, and we found that power pt for f equal to 50 hertz. We found that peak power cosine squared omega t. Okay, now we need to find power for f equal to 100 hertz. Well, if we look to the expression of power, the f is here, and if we increase f twice, the power will be increased 4 times, because power depends on the square of frequency. So the power dissipated at 100 hertz is 4 times larger than power dissipated at 50 hertz, and is equal to 4 multiplied power dissipated at 50 hertz, and is equal to 6201.2 multiplied cosine squared omega t. So as you can see, just by increasing the frequency, we are not increasing the current, we are not increasing the parameters of geometry of our system, we are just increasing the frequency. By just increasing the frequency, we can increase the power dissipated by our disk. Okay. Well, let's reconnect and continue, because we are out of time now. Okay, now the next problem. The next problem is saying, okay, let me copy all this and put here. Okay, so example 10.12, consider the thin conducting ring here, thin conducting ring, the flux density B equal to B0. So the flux density is B equal to B0 is constant and uniform throughout its cross section. At any given time t equals 0, the flux density B starts to increase as. So uh, at the very beginning, flux density B was equal to B0, and at any given time starting from t equals 0, the flux density changes with this law. Bt equal to B0 multiplied to 1 plus Kt, where K is constant. Calculate the induced current in the ring. Assume the ring is thin and the induced currents do not affect the magnetic field. Okay. Well, how do we solve this problem? Actually, there are two methods to solve this problem. First is the increase in the magnetic flux density causes an induced electric field intensity in the closed loop, and the second is the increase in the magnetic flux density induced the electric motive force in the ring. Well, let's start with the first method. Change in flux density produced an electric field, and this electric field produces the electric motive force. Okay, method 1. We are saying that change of magnetic flux, the figure B showing the relationships of electric field and magnetic flux density, and we use figure B in the method 1. Okay, we know the relationship between electric field and magnetic flux density by the equation of E d. Okay, I'm writing too large. So integral over the closed path C of E multiplied dr equals to integral over the surface S of minus dB over dt multiplied by ds, where S, or S prime in this case, is the surface defined by the circular ring, and C is the circumference of the ring. Okay. S is this, and C is this, is the circumference of the ring. Okay, let's compute these integrals. Let me open the new page. Okay, we are saying if we compute the first integral, it will be simply electric field. Now I'm writing without vectors, just the values. Electric field multiplied by 2πr and equals, if we compute this integral, will be equal minus p r squared dB over dt. And from this relationship we find that the modulus of electric field, I'm writing modulus just for the sake of simplicity. Modulus of electric field will be equal to, okay, P and P simplifies, R and R simplifies, R over 2, there remains R over 2, and of the T, instead of B we put B0 plus B0 KT, which is equal to R over 2. So the derivative of B0 will be 0, B0 KT will be B0 K. R over 2 K B0. Okay. Let me move it here. Let me scale down this as well. Okay. Well, we can write from this equation we go to this. Okay. And next we know that current density J equals to sigma multiplied by electric field, and this equals to sigma by K by R B0 over 2. Yes, over 2. And from this, the current, the unit of measurement is ampere per meter squared. And current will be J multiplied by S. Yeah. J is sigma K R B0 multiplied by S over 2. Here, okay, here we found the induced current in our ring because of the increase of magnetic flux density. This was the first method. Now we can use the second method as well. So here you can put numeric values and then find the numeric value for I. I will just continue with the second method. Okay. Second method is simply okay, the electric motive force was equal to the phi over the t, and from the previous lessons we know that dphi over the t is equal to dB over the t multiplied by ds prime, and this equal to pr squared b0k. And in order to find the current, we use Ohm's law. EMF is equal to R multiplied by I. From here, the current I, simply electric motive force over R, where R is the resistance of our ring, and is equal to L over sigma by S, and is equal to 2pr over sigma by S. Now the current is electric motive force is p r squared b0 k over r is so 2p r over sigma s, and is equal to sigma k r b0 s over 2. Well, this the same value for I which we found in previous from the previous method. Sigma kr b0s, sigma kr b0s, the same I. Okay. Well, save. Do you have any questions regarding these two problems? Okay, if you don't have questions, you may have a rest for, I don't know, for 5 or 7 minutes, and after the break we continue.